So now that we have a basic understanding of how to apply the fundamental theorem of calculus, let's get some practice with it. And so we're going to start off by just evaluating a bunch of integrals, and then we'll see some applications. All right, so first, let's see this one. We want to evaluate the integral from 3 to 6 of x minus 3 squared dx. All right, so the first thing we need to do is find an antiderivative. All right, x minus 3 squared, what we've learned to do with something like this so far is to expand the polynomial and then find the antiderivative of each term. So then this is equivalently the integral from 3 to 6 of x squared minus 6x plus 9 dx. Finding the antiderivative. The antiderivative would be 1/3 x cubed, right? So the antiderivative, so I'd have a 1/3 x cubed, 6x squared, 6, and I'd have an x squared over 2, and a plus, should be a 2 there, and a plus 9x. And then I would evaluate this from 3 to 6, and again, there's that notation. So if we clean this up a little bit, that's 1/3 x cubed minus 3x squared plus 9x from 3 to 6. Now, evaluating this at 6, subtract, evaluate this at 3. So I'd have 1/3 of 6 cubed is 216, yeah, minus 3 times 6 squared is 36, plus 9 times 6. And from that I need to subtract, substituting at 3, 1/3 of 27 minus 3 times 9 plus 9 times 3. 1/3 of 216, that is, so now let's bring out a calculator here, 216 divided by 3, that is 36. 36 minus 3 times 36 minus 108, plus 9 times 6 is 54. 1/3 of 27 is 9, minus 27, plus 27. So this all ends up being, let's see, 36 plus 54. So this all becomes negative 18 minus 9, and that's negative 27. A negative number. A negative number? Does that make sense? Is that reasonable? No, that's not reasonable. I did something wrong. How do I know that that's not reasonable? Well, if I think of this curve, right, understand, what does this mean? That's the area under a curve. All right, so if we think of the sketch of x minus 3 squared, x minus 3 squared, that's a parabola shifted 3 units to the right and opening up. And so it looks something like this. And so the integral from 3 to 6, here's 3 and here's 6, is this area that I just shaded. And that's above the x-axis. It can't be negative. I must have done something wrong. What did I do wrong? Let's see. Let's go through the calculations again. Every 3 cubed, 6 cubed is 216. That's good. That's good. 9 times 6 is good. That looks okay. Oh, there it is. 1/3 of 216 isn't 36. What did I do on my calculator? I did 216 divided by 6 on my calculator. That should be 72. That's the problem. All right, so let's clean this up. Should have been 72. All right, so now let's see. 72 minus 108 plus 54. That's 18 minus 9, which is 9. That's more reasonable. It's at least positive. All right, so one thing that we learn in mathematics is how to find errors and when to know that we've made an error. And so understanding what that integral means helped me understand that I made an error in the calculation. And that's okay. But it's important to know when it's important to know that you've made an error, and then again, you got to find it. All right, so let's look at this next exercise. Here we have the integral from 1 to e to the 5th of 1 over r dr. All right, well, 1 over r, the antiderivative of 1 over r is the natural log function, natural log absolute r. So I'd have natural log absolute r, and I need to evaluate that from 1 to e to the 5th. All right, e to the 5th is positive, 1 is positive, so I don't really need to worry about the absolutes here. So that would be the natural log of e to the 5th minus the natural log of 1. And so then that would be 5 minus 0, or 5. All right, so there's a couple of examples of how we evaluate integrals using the fundamental theorem of calculus, part 2. All right, so here's a couple. I'd like for you to try these on your own. So now would be a great time to pause. Let's integrate from 0 to pi sine x dx. The antiderivative of the sine function is negative cosine. So I'd have negative cosine x from 0 to pi. So then that would be negative cosine of pi minus, be careful here, negative cosine of 0. All right, so the cosine of pi is negative 1. So I have opposite of negative 1 plus, minus minus is plus, the cosine of 0 is 1. So that's 1 plus 1, which is 2. So what does this mean? If we think about this graphically, this means that if we were to draw the sine curve from 0 to pi, right? So here's pi and here's 2 pi, here's 1 and here's negative 1. So the sine curve, remember, does this. There's the sine curve, right? That's sine x. What this is telling me is that this region right here, that shaded region, is exactly, has area of exactly 2 square units. You know, all those pi's going around, and somehow it ends up being a nice integer. All right, integrate from 1 to 5, 1 over x cubed dr. Oh, so this is this is an error on my fault. These variables don't match up. So let's just change it to dx. So the integral from 1 to 5 of 1 over x cubed dx, well, that's the same as the integral from 1 to 5 of x to the negative third dx. All right, the antiderivative of x to the negative third, that would be x to the negative second over negative 2 from 1 to 5. All right, so let's see. Substituting 5, that would be, and one thing, let me adjust this a little bit. The negative 1/2 would be a common factor of the terms. So I can bring out the common factor here. I can bring out negative 1/2 and then just have the x to the negative second from 1 to 5. And that's a legal move. So then this would be negative 1/2 and 5 to the negative second. That would be 1/25 minus 1 to the negative second is 1. Right, because 1 to any power is 1. 1/25 minus 25/25, so that's negative 1/2 times negative 24/25. And so that would be positive 12/25. All right, here's a couple more integrals for you to try out on your own. Let's integrate from 4 to 36, 3 over the square root of x dx. One of our properties of integral says we're allowed to bring this factor in front of the integral. So this would be 3 times the integral from 4 to 36. And so now I have a 1 over the square root of x. So that's an x to the negative 1/2 power dx. So then that's 3 times, and the antiderivative of negative 1/2, or x to the negative 1/2, that would be x to the positive 1/2 over 1/2. All right, I can bring that, oh, and from 4 to 36. All right, so 3 divided by 1/2, that's the same as 6 times x to the 1/2 from 4 to 36. All right, so the 1/2 power is the same as the square root. So that's 6 times the square root of 36 minus the square root of 4. And so then that's 6 times 6 minus 2. 6 times 4 is 24. Integrate from negative 2 to 2, 4 to the x dx. This one's fairly straightforward. The antiderivative of 4 to the x is 4 to the x over the natural log of 4, and from negative 2 to 2. Again, I can bring that natural log 4 outside, so that's 1 over natural log 4, and then substituting the 2 and the negative 2, I would then have 4 to the second minus 4 to the negative second. And so that's 1 over natural log 4 times 16 minus 1/16, and we could simplify that some if we wanted to. 16 minus 1/16 is, if I get a common denominator and subtract the fractions, that would be 1 over natural log 4 times 255 over 256. So that would be a simplification, I suppose. All right, here's a couple more. Go ahead and try these on your own. Here we're asked to integrate x squared plus 1 from negative 4 to 4. All right, we find the antiderivative. So that would be 1/3 x cubed plus x, and we would evaluate that from negative 4 to 4. So let's see, so then that would be 1/3 of 4 cubed plus 4 minus 1/3 of negative 4 cubed plus negative 4. So let's see, 4 cubed, that's 4, 16, 64, that's 64 thirds. Plus 4, that's, I'll think of that as 12 thirds here. Minus, let's see, that would be a negative 64 thirds. And again, a minus 12 thirds. So notice that that is, what is that, 76 thirds plus 76 thirds. Those two values end up being exactly the same. And so it's 2 times 76 thirds. And so that's 152 over 3. 152 over 3. And let's do this next example. Here we've got the integral from negative 4 to 4 again. And we've got x cubed minus 16x. So let's see, the antiderivative would be 1/4 x to the 4th minus 16x squared over 2 minus 8x squared from negative 4 to 4. All right, so making our substitutions, let's see, that would be 1/4 of 4 to the 4th minus 8 times 4 squared minus 1/4 of negative 4 to the 4th minus 8 times negative 4 squared. All right, so let's see, 4 to the 4th is 64 times 4, 256 divided by 4. So that would be, what, 64 minus 8 times 16 minus 128 minus, well, that would be a negative 64. No, that would also be a 64. It wouldn't be negative in this case because negative 4 to the fourth is positive. So that would be a 64 minus 8 times 16 is again 128. And notice in this case, it's 0. So now these two examples are related to special types of functions. Notice that this function here, x squared plus 1, notice that this is an even function. X squared plus 1 is an even function, and x cubed minus 16x is an odd function, where I hope you've learned about even and odd functions in your algebra classes. And so it turns out that there's a special property for even and odd functions. If f is even, then the integral from negative a to a of f of x dx is twice the integral from 0 to a of f of x dx. And if f is odd, the integral from negative a to a of f of x dx is exactly 0. So that's a nice property to be aware of. If you notice an even function or an odd function, it might be able to help you evaluate the integral a little bit. But you don't have to rely on this property. You can always evaluate it using the other techniques. All right, so now that we've got some practice evaluating integrals, let's see some examples, some applications, I should say. Find the area under the curve f of x equals x squared plus cosine x over 0 to pi over 2. Now notice, it doesn't say approximate the area. It says find the area. So to find the area, here we're assuming exact. If we want to find the exact area, then that would be the integral from 0 to pi over 2 of x squared plus cosine x dx. That's what that means. To find an area means evaluate an integral, right? If we're finding an area under a curve over an interval, that's an integral. So then we find the antiderivative, 1/3 x cubed plus sine x from 0 to pi over 2. All right, so substituting pi over 2, I'd have 1/3 of pi over 2 cubed plus the sine of pi over 2 minus 1/3 of 0 cubed plus the sine of 0. All right, so let's see, 1/3 of pi over 2 cubed, that's pi cubed over 8. So that's pi cubed over 8 times 3 is 24. The sine of pi over 2 is 1 minus 0 cubed is 0. Sine of 0 is 0. So this area is pi cubed over 24 plus 1. Suppose an object is moving in a straight line, or moving along a straight line. If the velocity of the object is given by v of t is negative 32t plus 120 feet per second, find the displacement of the object over the time interval. So displacement, if you're not familiar with that term, the displacement of an object is its change in position. A change in position over that interval. All right, so let's say that the position function is s of t. Well, then the change in position would be s of 10 minus s of 0. The position, the end position minus the initial position. Well, now wait a second. How are position and velocity related? Well, if we remember, the velocity was the derivative of the position function. And so this turns out that the position at 10 seconds minus the position at 0 seconds, hey, isn't that the integral of the velocity over 0 to 10 dt? Right? Because if we think, how would we go from the velocity to the position function? We would find an antiderivative. And so note and remember that v of t is s prime of t. Okay, and so now we can find this, right? So v of t, s prime of t, so what we would do is evaluate the integral from 0 to 10, negative 32t plus 120 dt, and so that would be negative 16t squared plus 120t from 0 to 10. All right, substituting 10, that would be negative 16 by 100 plus 120 times 10. Substituting 0, I hope you can clearly see that it'll be 0 if we substitute 0. So that's negative 1600 plus 1200, that would be negative 400 feet. So the displacement is negative 400 feet. Now this is an example of what's called the net change theorem. The net change theorem says a new value of a changing quantity equals the initial value plus the integral of the rate of change. The new value, f of b, the new value of a changing quantity equals the initial value, f of a, plus the integral of the rate of change. So notice that this is just really a restatement of the fundamental theorem of calculus, where the idea is that if we have a change, if we have a changing quantity, then the net change over the interval is just the integral of that quantity, right? So the integral, the net change, right, f of b minus f of a, is simply the integral of that changing quantity, that f prime of t dt. All right, so that's called the net change theorem. Now let's look at a slight variation on that same problem. So same setup. The object is moving along a straight line, and the velocity is given by this v of t. But now it says instead, find the distance the object travels over the time interval. Not the displacement, not just the change from its beginning position to its end position, but now the actual distance the object travels. So in a sense, in our previous problem, we had a starting point somewhere on the line. And, all right, so here's the start point. And the end point was over here, where this distance, right, where this change was negative 400 feet. Okay, but now let's think about this. The velocity function was negative 32t plus 120, and certainly at time 0, the velocity was positive. And so if we sort of think about it that it was traveling on a straight line, and if we take this line, if we take the positive direction to be to the right, what actually happened was the particle was moving to the right first, and then started moving to the left, and then ended up where in the end point. And so that 400 is not the actual distance the object traveled, just its displacement, just the change in position. And that's different from the total distance traveled. So now the total distance traveled. All right, so let's take the positive position to be to the right, or positive direction, I say. Let's take the positive direction to be to the right. So then it was moving to the right, so the particle, the object, is moving right for when v of t is positive. All right, so now for v of t to be positive, we would need the negative 32t plus 120 to be positive. All right, so let's see. So then that means then that t is less than 120 over 32. Well, negative 120 over negative 32, yeah, if we're following the order there. So that's 3.75. T is less than 3.75. And so then it's moving left when the velocity is negative. And moving left so that ends up being when the time is greater than 3.75. And so in a sense what we have to do here is we have to break up this single integral into two integrals. And we have to be careful here. So what happens here is we're going to integrate not the velocity function, but the absolute value of the velocity function. And we're going to integrate it from 0 to 10 dt. Now what we notice is the velocity function changes at 3.75, when t is 3.75. And it's positive when over the first piece from 0 to 3.75. So v of t is positive here, and v of t is negative when t is greater than 3.75. So I'm going to integrate from 0 to 3.75 the negative 32t plus 120, right? Because that's where the velocity is positive dt. But now, then the absolute, if we think about how absolute values work, it would take any negative values and turn them positive. So now, plus the integral from 3.75 to 10, and I would now have the opposite of the negative 32t plus 120 dt. And so then we evaluate each of these integrals separately. I'm not going to go through all of that work. I'm just going to give values. So I've calculated those values off camera, and this gives me 225 for the first integral, feet. And then for the second integral, it's 625 feet. And so then the total distance traveled is actually 850 feet. So when you're calculating a total distance traveled, you integrate the absolute value of the velocity function. You have to figure out when the velocity would be positive or negative, and you have to, in a sense, use the opposite of any times when the velocity would have been negative. All right, so one more application here. Suppose that air is pumped into an empty balloon. The air enters the balloon at a rate of 3 root t cubic inches per minute. Find the volume of the balloon after 9 minutes. All right, so now would be a good time to pause. Try this one out on your own. All right, the air enters the balloon at a rate of 3.2 cubic inches per minute. The change in the volume is 3 root t cubic inches per minute. If we wish to find the volume of the balloon after 9 minutes, this is just an application of the net change theorem. So let's integrate from 0 to 9 the rate 3 root t dt. So that would be 3 integral 0 to 9 t to the 1/2 power dt. So that would be 3 times, let's see, t to the 1/2. Antiderivative of t to the 1/2 would be t to the 3/2 over 3/2 from 0 to 9. I can bring the over 3/2 out, so 3 divided by 3/2 is 3 times 2/3. That would be 2 times, and then I would have 9 to the 3/2 minus 0 to the 3/2. 9 to the 3/2, that's the square root of 9 cubed. The square root of 9 is 3. 3 cubed is 27. 0 to any power is 0, so I'd have 2 times 27 minus 0, so 54. And the volume, it's increasing by cubic inches per minute, so then it would be cubic inches would be the volume. Okay, so just an application of the net change theorem. All right, so that completes this this part of the fundamental theorem of calculus. This is more on the actual use of the fundamental theorem. All right, so so now you got to go practice this a few times. I want to mention one other thing, and that is that your calculator can evaluate these. Graphing calculators have these capabilities, and depending on your calculator, you might have different instructions. But on the TI-83 or 84 calculators, here's how we can do this. So let me just evaluate. I'm just going to evaluate the integral from 0 to 9 of t to the 1/2 dt. If you go to the math menu, the 9th option says FNINT. This is a numerical integration. And if we hit enter on this, the call is, all right, so what we have to type in now is, so it brings up the FNINT on my home screen. I have to type in the function. Now, I can use t, but remember, it's a dummy variable. I can use whatever variable I want. I'm just going to use x. So I'm going to use x to the 1/2 power. X to the parentheses 1/2, comma, what variable am I integrating with respect to? I'm integrating with respect to x, comma, what is the lower limit? 0, comma, what is the upper limit? 9. Close it off, hit enter. Okay, 18, and yeah, that's correct. So, right, if I took this, right, this expression right here, this would be then 20. This would be 27. So this would be 9 to the 3/2 over 3/2. Minus 0, And 9 to the 3/2, that's 27 times 2/3 is 18. All right, so that's where that 18 comes from. All right, now if you have a newer version of the TI-83 or 89 calculators, it may be in what's called the math print mode, where it makes things look nicer. So if I switch the calculator over to math print mode and I hit the same call, if I hit math and the 9th option, it brings up that nice little integral format template, and we just type in the 0 and the 9, and we would type in the x to the 1/2. I'll just use a 0.5 instead here instead of 1/2 dx. And that gives us back the 18 as well. Now, if you have a different calculator, you will have a different syntax. You'll have a different way to type this in. Now, understand, this is not work. Typing that into your calculator does not show me that you know how to use the fundamental theorem of calculus. And so there will be points on any tests where you might be allowed to use this, but there are points where you're not supposed to use this, and you're supposed to actually show the appropriate work. Okay, so be aware of that. All right, I guess that's it for this one.